Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another lecture, Math 1203. Well, lecture. Today we're going to just have a Q&A session because in my experience, the kind of things I dealt with um, lectures 6, 7, 8 in that area, they tend to be lectures that are at least at first, weird for students conceptually. So I just wanted to make sure that we all understand what's going on. I wanted to have this check-in with you guys because you have a quiz at the beginning of your next lecture. So I just want to make sure you guys have a fair shot at that. And let's actually just jump in here. So we do have okay. Yeah, so let's actually get started. Maybe any questions you guys have so far, anything that you've seen in these lectures. So I believe since the last time since the last time I met you, you should have covered since then topics like average rate of change. I spoke a little bit about the main branches of calculus and what calculus is and all that stuff. But then we started the topic of limits. We spoke of one-sided limits, what limit really means, infinite limits, limits at infinity. We spoke about a limit strategy, like so when we want to compute a limit, what are some of the ways that we can do that? We spoke about continuity. We spoke about someone else trickling in here. The elementary continuous functions, properties of limits, definition of derivative and tangent lines. We actually started that in lecture 8. So I just want to make sure that all of that was well understood. At first, I'm going to just throw some questions out. Any questions on any of that?
Yeah, since it's like so much material, what can we kind of expect the breakdown of the quiz to be? Like in terms of
pretty much the what I mentioned just now. So, I have red for some reason. So, quiz next class. So, things I would expect you to know is how to compute average rate of change. You should know about, in general, what are limits and how to compute them. You should know about what is continuity. And how to determine a function is continuous or continuous at a point. You should know, what else? Definition of a derivative. And compute one. As well as how to find tangent lines.
Is it any of the stuff from the last quiz? Like, is it cumulative or no?
No, so quizzes aren't cumulative. Tangent line to a function at a point. So in a broad sense, these are the topics that the quiz would cover. And of course, I expect you to be able to deal with these topics in various situations. So for example, when I talk about limits and how to compute them, I mean, you should know how to talk about a limit if I give you a picture of a function and ask you, oh, what is the limit at this point? Or if I just give you an actual formula for something that asks you, find the limit as x approaches this thing of this function. So you should understand conceptually what these things are about, as well as how to compute them, as well as how to look at a picture and talk about that picture in terms of these things. But I guess those are the five main topics that will be tested. I might throw in some bonus problems. I believe I did last time as well. And it might be on things like second derivative. So this is like when I'm getting into lectures 9 and 10, etc. Second derivative, concavity, and the derivative rules. So we're going to start learning things like product rule, chain rule, quotient rule. But these are future lectures, right? So this is after lecture 8, chain rules, quotient rule, etc. Right, so remember bonus, you should have seen this on your last quiz. Basically a bonus is, it's not really something I expect you to know for the quiz itself, meaning if you don't know about these topics, you can still get 100% on a quiz. However, you have the opportunity to get some extra points, and it's on topics that have not yet been covered as so far as the lectures have gone so far. So pretty much the bonus points is a way to reward students for reading ahead. I guess it's also just sort of a mercy to people who have taken the class before. And so I'm going to try to give you a boost so that you get some extra points to make sure you never have to take it again. Either way you want to look at it, it's just a chance to actually get beyond 100% on a quiz. And in general, what do I do with those bonus points? Well, bonus points in a category will roll over to things in that category. So for example, anything you get above 100% on any quiz, I'll take those extra points and I can add it to some other quiz that you didn't do so well in. So let's say we have 2 quizzes where each of them are 10 points and each of them had 2 bonus problems. Let's say on quiz 1, you got 8 out of 10. And then on quiz 2, you got 12 out of 10, meaning you got everything right, plus you got the 2 extra bonus points. What happens is I can take those 2 extra points, the extra 2 points that you got from quiz 2, and I can add them to quiz 1 after the fact. So then your average grade would actually be 10 out of 10 on both quizzes, if you look at it that way. Because I'll take 2 extra points that you got from quiz 2 and I'll add them to quiz 1. And so it kind of, it helps you beef up your grades. So you get rewarded, in other words, for reading ahead, working just a little bit harder than your peers. I want to actually reward that. So that's how that would go. So up to lecture 8 actually talks about everything that I wrote down above the bonus line. So lectures 3 through 8, that's the stuff that they covered. But the next few lectures, lectures 9, 10, 11, moving forward, I talk about the second derivative, I talk about concavity, I talk about derivative rules. Okay. I believe I answered your question and a little more there. So if there is anything I said you didn't get, let me know. Maybe any other questions?
Could you go over limits when x equal to approaches plus or minus
Hold on.
infinity?
I think someone's talking in the background or needs to be muted or something.
Okay, so
Okay, I think they muted. Okay, so who was just asking the question?
I was asking a question. I said, could you go over limits when x approaches plus or minus infinity?
You mean in general, or do you have a specific example in mind?
In general, I don't get that.
Oh, so when you say limit as x approaches infinity of f of x, so these are called and limit as x approaches negative infinity of f of x. These are called limits at infinity. So this is what the y value approaches as x goes to infinity or x goes to minus infinity respectively. So pretty much in one of them, respectively. In one of them, you just imagine that your x value, your input value is just getting bigger and bigger and bigger and bigger and bigger. And what's going on as you move to the right. And one of them is when it gets smaller and smaller and smaller. So for example, I can ask you, what is the limit as x approaches infinity of the function e to the x versus the limit as x approaches negative infinity of e to the x? Well, there are a couple ways you can do this, but probably the easiest way of the limit strategies that we did was to just know the graph of e to the x. We know what that should look like. That graph looks like this. Goes forever in both directions. So the left side, as you're going off to the left side, it's getting closer and closer to the x-axis. It never touches it. As you go off to the right side, it starts to shoot up and it increases very quickly, faster than any linear function. In fact, faster than any polynomial that you could ever come up with. So that's the basic graph. So now when you're looking at x goes to infinity, so what you're basically doing is worrying about, here's your x-axis, and you're just imagining as x is going off into infinity, what is y doing unambiguously? You'll notice that as your x value gets larger, your y values just keep getting higher. And so we'd be able to say something like, the limit as x approaches infinity of e to the x is infinity, because the y value here is just keeps getting bigger and bigger and bigger. Okay, so you just look at as x goes off to infinity, what are the outputs doing? Is there a behavior of the output that I can say unambiguously what it's doing? So is it approaching some specific number, or is it just keeps getting bigger and bigger and bigger, or something else? I mean, in that sense, if I were to ask you to make sure you have the concept here, what is the limit as x approaches negative infinity of e to the x? What would you say the answer is?
Would be negative infinity.
Are you looking at the picture?
Yeah.
What is happening to the y values as my x goes to the left?
It goes y equal to y is infinity. It goes positive infinity.
As x goes to negative infinity?
Yeah.
So x goes to negative infinity means I'm looking at the left side and I'm looking at, so here's my x, and I'm looking at x goes to infinity. X is moving this way and you just keep going, right?
Yeah.
And you're looking at what the y value is doing. Now, if you say the y value is going to infinity, what you're saying is the graph is going up, right? But is the graph going up?
No.
And if you say
It's
negative infinity,
decreasing.
what that means is the graph is going down, like keep going down forever. And
Oh,
is
so
that
it's
true?
equal to 0, right?
Well, what you would say is that the y value approaches 0, right? So it's not equal to 0. So it never actually
Okay.
gets there,
Okay.
right? But as far as the limit is concerned, remember, this was an important concept with limits. You don't have to be equal. So I probably don't want you to use that word unless you preface it by the limit is equal to this. All right, so that's actually 0. Because if you start looking at what the y values are doing, if you look at the outputs as you're along this function moving to the left, those dots get closer and closer to the line y equals 0. Whereas if you look at the coordinates on this graph here, as x is moving to the right, those guys will approach infinity. Approach infinity means they just keep getting larger and larger and larger without bound. So suppose I had a graph like this. So this here, it's not a part of the graph. This is an asymptote. Let's pretend this is at y equals pi over 2. Let's see this here. Let's say this is x equals 1. And the graph looks like that. And then here, let this be where y equals 1. And the graph goes like that. Okay. Now, what if I were to ask you, what is the limit? So this is the graph of f of x, right? What is the limit as x approaches infinity of f of x? What is the limit as x approaches negative infinity of f of x? And what is the limit as x approaches 1 of f of x? Let me fill this in here.
Which one is
Okay.
it, the vertical or like horizontal
What
ones
would we
that like?
say here? Come again?
What were the limits that you can cross? Isn't there ones? There's one. If it's, I don't think it's vertical. Oh, shit, never mind. Sorry.
I mean, crossing a limit isn't really a concept. I think you're thinking of asymptotes, maybe?
Oh, okay, yeah, you're
Horizontal and
right.
vertical
I am.
asymptotes?
Yeah, I am.
Yeah, those aren't, I mean, their definitions involve limits, but it doesn't have to do with the limits themselves. There's no such a concept of, oh, we can cross this limit, but not that limit. But let's look at this one here. So this is a function. This is a picture of a function here. And what would you say these limits are? If I were to ask you, what is the limit as x approaches infinity of f of x?
Is it pi divided by 2?
It's pi over 2. Why? Because you're tracking the y values as x gets closer and closer to infinity. So you'll notice here, as my x goes off to infinity, my y gets close to pi over 2, because here's the pi over 2 line, and my graph gets closer and closer to that line, right? So my outputs are getting closer and closer to pi over 2 when my x values keep getting larger and larger and larger and larger. So that's why this is the answer here. So when you're talking about limit as x goes to infinity, what you're doing is you're looking at the far right side. How far? As far as you can get it. And when you think you've gotten there, keep going, right? Never stop. Look all the way to the right, keep going to the right, and then you're looking at what is the y value doing? Is it doing something that I can specifically say it's going towards this number, or it's going up without bound, or is it going down without bound? If you can't tell what it's doing, then you cannot answer the question. Okay. What is the limit as x approaches negative infinity?
Is it negative infinity?
It's negative infinity. And why is it negative infinity? Well, notice that as my x is going this way, what's happening with the y values? See, the y values are going down. Without bound, right? They just keep going down. Down, down, down forever. So my y value is just going down. We represent that by negative infinity. That's how we talk about that concept. Right, so when we're looking at the y values, infinity for the y values just means you keep going up and up and up and up and up and up and up. Negative infinity for the y values means you keep going down, 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 down. When you're looking at the x values, x going to infinity means you're moving to the right, 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 keep going right. And when x is going to negative infinity, you think of that as that means you're going left, 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 left. So basically, when we say the limit as x approaches infinity of f of x, we're saying if we move far to the right, how is the y value behaving? If we say x is going to negative infinity, we're saying if we move far to the left, how is the y value behaving? Okay, so hopefully that's clear. Now, what is the limit as x approaches 1 of f of x?
Is it does not exist?
Why would you say that?
Because the limit from the left side is approaching 1, but the limit from the right side is approaching negative infinity. And since they're approaching two different values, that means it doesn't exist.
Right, so if you look at here, if I'm approaching 1 from the right, which is that little notation, I put a plus here, it is going off to negative infinity. That's because over here, the graph is going down, down, down. As x gets close to 1 from the right, my y value goes to negative infinity. It keeps going down. While, how many more colors can I do here? I forget. I'll just keep it in blue. While if my x is approaching 1 from the left side, which means I'm coming from this side, my y values, you'll notice, will approach 1. So as I'm on this graph here, getting close, my x value is getting close to 1 from this side, the y value is getting close to 1. So here I'd have the limit as x approaches 1 from the left side of f of x. That is 1. These do not agree. And therefore, I would say these are not the same because negative infinity is not the same as 1. And therefore, because they're not the same, I would say the answer to this limit question is D and E, does not exist. I mean, any questions on this example here? Maybe I'll do another example. Maybe look at this idea. Oh, it's a horrible line. Not much better. But let's go. So here's a function. And here's how it's behaving. So it's an open circle. Here's a closed circle. So there is some, want this to hit some asymptote going forward, some asymptote going that way. Just making up this example as I go. Okay, so this graph bounces. Boop, 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 boop. Keep going like that, right? Let's say this is at 2, that's this horizontal line. This is at -1, that's this horizontal line. Okay, so that's my graph. If I were to ask you, what is the limit as x approaches -infinity of our function here? What is the limit as x approaches positive infinity of f of x? What is the limit as x approaches, let's call this 2, and let's say this is at 1 of 2 of f of x. Let's make that 3. So you'll know what 2 I'm talking about when I give you an answer. Okay, maybe someone who didn't answer before.
For negative infinity, wouldn't the limit be 0?
Okay, and for positive infinity?
2.
And as we approach 3?
Does not exist.
Are you
Doesn't
sure?
exist.
I mean,
Well,
it's filled in at 1 though, right?
But
Are you seeing that? Did you see it shaded?
Yes,
And?
but there's a open dot at 2.
Yeah, but I know that f of 3 is 1, right?
Yeah.
So I mean, do you want to change your answer?
Hold on. I'm confused.
Okay. What are you confused about?
So I thought because there's an open dot at 2, then the limits as they're approaching 3 don't agree, and therefore it would be does not exist.
Okay, so as you're approaching 2, what limits are you talking about?
But is it so? Because f of 3 is 1, you can they're defined there. So
So what are the limits that you said don't agree?
like as it's approaching 3 from the left, it's going to 2 where you have the open dot, and as it's approaching from the right, it's going to 1 where you have the closed dot.
Okay, so your answer would be what?
Does not exist.
Does not exist. Yes. I was playing devil's advocate. You got that. You got that right before. I wanted you to know that that's the answer. Because sometimes what happens is students second guess themselves on tests, and they're like, wait, I'll go back and change my answer. And then they change it to the wrong answer. So remember, a very, very important concept with limits is that it does not care about what you are at the point. The limit does not care about being at the point, which means if the question I'm asking you is about limits, it does not matter who's shaded and who's not. You don't care, right? That's what I want to make sure that you're doing. So a problem like this is just to kind of catch the student who doesn't pay attention to that concept. I would know from experience, there are, I wouldn't say a lot of students, but a hefty 30–40% of students might have said 1 is the answer here, but it's not, because filling in the 1 is irrelevant. The limit does not care about being at the point, it cares about being close to the point. That being said, there is an error here. So that one, problem 3 is actually correct. Problem 3 is actually correct. And the reason that that's correct is because, let me actually write it down. So problem 3 is correct because if I take the limit as I approach 3 from the right side, I would get 1. And if I take the limit as I approach 3 from the left side, I would get 2. And those two are not the same. So that means does not exist. Okay, so that one is right. However, there is an issue here. Maybe someone else can jump in here, tell me what's the issue. So it means that something is wrong with one of the first 2 answers.
The limit as x approaches infinity should be does not exist.
Why not? Why? I mean, the graph is there, right? There's no hole, there's no anything. Why? Why would you say it does not exist?
Because it fluctuates between 2 and -1.
Right. So it just keeps bouncing up and down, and it's achieving all values between -1 and 2, right? Which means, and again, this is leading to another very important concept of a limit. You have to be able to say without ambiguity what the y value is doing. So it turns out that if someone said 2 is what the y value is getting close to, that person would be right an infinite number of times. However, if someone said -1, they'd also be right. And if someone said, oh, 0, they'd also be right. There's a lot of ambiguity here. There is no one thing that the y value is getting close to. The y value is bouncing between 2 things. So at any point in time when you stop in the future, there's no telling where you will stop. There's no telling I'm definitely at 2, or I'm definitely at -1, or I'm definitely at 0. You don't know, because things are just bouncing up and down. It's not settling, right? The limit is going to tell you what you're getting close to, what you're settling towards, and it should be unambiguous, right? So the actual answer is here is does not exist. And the reason is y value doesn't approach anything. It oscillates between 2 and -1. Or I should say -1 and 2, but whatever. Yeah. Okay. So this is how like a picture can really start to pull at, do you really understand what the concept of a limit is, right? What does it actually mean for a limit to exist? What does it mean for a limit to be a number? What does it mean when a limit does not exist? How would you be able to tell it does not exist, right? So yeah, one easy way is if you are getting, if you're approaching, x is approaching a certain specific value, and from the left and right, you're getting different outputs. Your outputs are getting closer and closer to different things, you can say the limit does not exist. But also, if you can't actually specifically say what the y value is getting close to because it's bouncing up and down or it's doing something crazy, you also can say the limit does not exist. Like there's no way to tell what the y value is going to do as I'm getting to some point. So yeah. So those are some very important concepts of limits, and yeah, there is some confusion that should happen here. So I want to make sure that people are aware. There is a difference between being evaluated at a certain point. So for me to say f of 3 is 1, it's different from me talking about the limit as we approach 3. So f of 3 and the limit as x approaches 3 of f of x are not the same thing. In general. So that you should definitely know. That's a very important concept, meaning limits do not care about being evaluated at the point. Now, another important concept, occasionally, we'd have something like the limit as x approaches 3 of f of x is the same as the output of the function. Now, when that happens, what do we say? So if I were to tell you the limit as x approaches 3 of f of x is actually the same as the output of f at 3, when I plug in 3, it gives me the same output that the limit does. What is that saying? What concept is that describing?
It's describing continuity.
Continuity, more specifically?
That the function is continuous at that point.
Right, this means f of x is continuous at 3, right? Now, this is a very important point. So whenever your limit equals the value of the function, the output is the same as the answer that you get for the limit. We describe this kind of scenario as being quote unquote continuous. It's a very, very important scenario. Why is it important? Because it turns out for calculus, the thing that we will be getting into, if your function is not continuous at a point, you can't really do calculus there. Now, there's some way that you can talk about integration, but that's outside of the scope of this class, where an integral would exist, even where functions aren't, on intervals where functions aren't defined. But for our intents and purposes, if we're not continuous at a point, we can't do calculus. We can't find a derivative there. We can't find a tangent line. We can't do a lot. There are a lot of things that we won't be able to do. So knowing where functions are continuous, what that means as a concept, how can you tell on a picture, is going to be very important. So for example, I can have a picture like here where there's a hole, right? So let's say this is at 3 versus this is actually filled in. At 3. So let's say this here is at 1. Let's say this here is at 1. So here what you'll realize is that the limit as x approaches 3 of f of x is, what is it?
1.
It's 1. What is f of 3?
Does not exist.
Right. When we're talking about outputs, we usually say undefined. Over here, you'll notice that the limit as x approaches 3 of f of x is 1, and the limit and f of 3 is also 1. So in this case, we can say continuous at 3. In this case, we say it's not continuous at 3. Or another way of describing that is that we can say it's discontinuous. Okay, so there are times when the output of the function coincides with what the limit is. Whenever this happens, it's very nice because it means, and again, just because it's continuous doesn't guarantee that we can do calculus there either. We'll talk about that later on. But if we're not continuous, it definitely means our calculus is going to break down. So it's very important of knowing what it means to be continuous and all that good stuff. So here is what it means to be continuous at a point. What does it mean to be continuous in general?
Does it mean that the function is like is not undefined at any points?
If
it's continuous at every point in the domain.
Right, if it is continuous at every point in the domain. That's the phrase I wanted to do. If it is continuous at all points in its domain. Which means this equation works out, i.e., for all points x equals a in the domain of f, we have that it's true that the limit as x approaches a of f of x equals f of a. So continuity at a point means you're checking this equation at a point. If it turns out this equation is true for all points in the domain, we call the function a continuous function in general. So there are many continuous functions. There are 6 basic, fundamental, elementary continuous functions. These are the guys that are going to build up all the functions that we can do calculus with, at least at this level. So these are the polynomials, the rationals, the radicals, the trig functions, exponentials, logarithms. I think I got all of those correct. In this class, we're not going to focus on trig functions at all, so you don't really need to know about trig functions, but you should know of their existence, at least in theory. And these are all functions where this limit equation works out at all points in the domain. Basically, intuitively, what this means is that you can sketch it without lifting your pencil off the page. There's no gaps, there's no hole, there's no breaks, there's no jumps, there's no disruptions. However, that is not a mathematical definition. Mathematically, what that means is that this equation is true for all points of the domain, right? And there are times when you won't know what the picture looks like, but you need to know that something is continuous at a point for you to do some calculations. But the function itself is very complicated. You might not know what the picture looks like. So yeah, if you have a picture, it should be easy for you to tell where a function is continuous versus where it's not. However, you should be able to tell this based on the formula and by computing limits. Continuous at a point just means the limit coincides with the output. But it's very important that you know, in general, this is not true and this is not to be expected. The output has nothing to do with the limit in general. So your function can have an output and the limit is something else. Your function can have an output and the limit is does not exist. You can have the function being undefined, but the limit exists. And any combinations of these, they do not have to be the same. But when they when they are the same, when the output is coincidentally the same as the limit, we call that serendipitous event continuity. We say it's continuous there, and intuitively what this means is there's no disruption, there's no hole, there's no break, there's no gap. Mathematically, it means that this equation, an equation like this, holds for all points in the domain of a function. So that's what continuity means, and hopefully we are aware of that. Another important concept. Tell me about the definition of the derivative. How would you define a derivative? How's a derivative defined? Let's talk about maybe, I don't know, intuition might be the wrong word. Or let's talk about synonym. So conceptually, what is, when you say, I'm talking about the derivative of f of x, what am I talking about? What is a synonym? Give me some sort of equivalent expression or concept.
Like the slope of the tangent line?
Right, it's the slope. Right, so derivative is slope or slope of tangent line. Or rate of change. Right, so that was the whole point of a derivative. We wanted to measure the rate of change of something, and it turns out, mathematically speaking, we could think of this concept as being equivalent to some sense, the slope of a function. But not just the slope. Slope was something that we had that had to do with straight lines specifically, but when we generalize that concept to general functions that might not be straight lines, we need a bigger word for that concept. We call that word the derivative. So derivative is synonymous with slope, and it's just a measure of rate of change, how fast one thing is changing comparable to another thing. So yeah, that was the intuition. Now, what is the mathematical definition? If I asked you about the derivative at x of f of x, how did we define that?
Well, I mean, you could say that it's the limit as h approaches 0 of f of x plus h minus f of x over h.
Right, so it's the difference quotient, but it's the limit of the difference quotient as the denominator approaches 0. So this is why the difference quotient was important, which is why in classes way before calculus, when you're in algebra and pre-calc, you've probably seen this expression many times over, and it might have seemed very random to you, but it turns out it's not random at all. This was an expression, f of x plus h minus f of x all over h, was an expression for the slope of the secant line. And it turns out that when you push the 2 points together from the secant line, you can achieve what we call a tangent line. And mathematically, how we push points close together, we use the concept of a limit. This is why the concept of a limit is defined the way it is. We want the idea of moving close to something without actually achieving that thing necessarily. Just what are we approaching? This idea is very, very useful. It's one of the big ideas in calculus, the idea of getting close, inching closer and closer to something, and we can call that. What was the notation? Do you remember we had a shorthand notation for this?
F prime of x.
Right, it's f prime, and f prime looks like a little apostrophe.
And dy dx.
Right, also something like dy dx if we set y equals f of x. Right, so the dy dx, this is called the Leibniz notation. It's kind of like you use this fractional notation to represent the derivative. And it turns out that notation is actually pretty convenient because there are a bunch of contexts in which you can actually treat this guy formally as a fraction. You can think of the dy as being the numerator and the dx as being the denominator. And there are going to be times in this class where it's going to be very convenient to actually think of it that way and move dx's and dy's, but also in future math classes like differential equation, which if any of you are going into chemistry or any other sufficiently mathematically complicated fields, you're going to need that concept of the derivative as well. The fact that you can actually think of the derivative as a ratio of the change in y over change in x. The prime notation, this was the notation that Isaac Newton used. It's called Newton's prime notation. So that is the definition, the mathematical definition of a derivative. If you want to compute the slope of a function at a certain point, x, this is how you would do it. You find that limit. And that's just a definition that you should know by heart. So if I were to ask you, use the definition. Compute f prime of x if my f of x is, let's say 1 over x plus 2. How would that look? So this means f prime, you'll start out with the okay, how would that look here?
Would you do 1 over x plus 2 plus h, and then I put that in parentheses?
That is correct. Coincidentally, I'd rather you say it differently though.
Do you want me to combine like one fraction?
No. I mean, I would rather you not put the h at the end. In this case, it's actually the same, but I want you to remember thinking of f of x plus h as in you take all x's and replace it with h.
Okay.
Right? So there is the very real possibility of someone thinking, and I believe this happened this semester already, that f of x plus h just means you write down, copy down f and then attach an h at the end, plus h. That is incorrect. F of x plus h means in every instance where you see x, you now write x plus h, right? So going with that concept, I'd rather write it this way. Now, in this case, x plus 2 plus h is exactly the same thing, but conceptually, I do want you to think of it as replacing every instance of x with x plus h. Then we would subtract f of x all over h. How would I actually simplify that?
I would, you could multiply, like to like get the fractions, like get rid of the fractions. So you could multiply by like the common denominator of the two of them.
Or the LCD, which is what in this case?
It would be x plus h plus 2, all like in parentheses. And then times x plus 2.
Right, and you multiply and divide by that because you don't want to actually change the answer. Now, of course, this whole thing here is going to multiply the two top functions by the distributive law. And then this one, I'm going to just multiply the bottom function. Okay, so then this here would become the limit. And I want you to notice that I keep writing this limit symbol because I'm not actually taking a limit yet. I'm actually just simplifying. So here, in the first case, the x plus h plus 2 will actually cancel the x plus h plus 2, and so you're left with x plus 2. Minus, in the second case, the x plus 2's would cancel, and you'd be left with x plus h plus 2. And of course, the parentheses are important here. All over h times x plus h plus 2 times x plus 2. And I'd throw in a reminder here because it's actually something I see quite commonly. And it can lead to errors. Never expand the denominator. You want to keep the denominator factored, and even if it's not fully factored, chances are you'd want to factor the denominator further, because you are going to want to know when certain things will cancel out, because simplifying is very important. So in the top, what do I have? I have x minus x. I have 2 minus 2. And so in the top, I would have just minus h. In the bottom, I have h. Now what? What is that limit?
Would you cancel the h's first?
Right, you'd cancel the h's. Now what?
So now you could plug in 0 for h in the denominator, and you would just get x plus 2, all of that squared.
Right. So that is the answer. And it turns out that this gives the slope of f at any point x in the domain. Right? So for example, x equals 1 in this domain. So remember, our f of x was 1 over x plus 2. Now, if you were to draw that picture, this has an asymptote at minus 2, and then the graph looks like this. Now, if someone were to ask, what is the slope of the tangent line? When x equals 1, what would you say?
Is it 1/3? Or no, it would be negative 1/6.
Right. So what you 1/6? What you do is you plug in x equals 1 into f prime. So this means you would actually compute f prime evaluated at 1, which is minus 1 over 1 plus 2 squared. So that would be minus 1/9, right? And so basically what that means is if I were to draw a tangent line here, so if I were to draw a line, a straight line that locally touches it in one point in such a way that if I zoom in, that blue line and that graph, so the tangent line, will behave the same way, then the slope of the line that would accomplish this feat, meaning it approximates the function at that point. What does approximate mean? The closer I zoom in on this region, the more I zoom in, the closer and closer the straight line is going to look like the graph, okay? Now, the straight line that would accomplish this is the line that passes through that point and actually has the slope of minus 1/9. What if I were to ask you, what is the equation of the tangent line? Okay, so again, let's go up. Here's my function. F of x is 1 over x plus 2. here's my derivative. F prime of x is minus 1 over x plus 2 squared. I asked the question, what is the slope when x is 1? We found that to be minus 1/9. If I were to ask the question, what is the equation of the tangent line at x equals 1? How would you answer that? Just to remind you, f of x here is 1 over x plus 2. F prime of x is minus 1 over x plus 2 squared.
So you would plug in x equals 1 into f of x to get the y value.
Okay, so when x equals 1, our y equals
1/3.
1/3. Okay.
So now you have a point, 1 comma 1/3.
Right. So basically what that means is the point 1 comma 1/3 is on the graph.
Mm-hmm.
Okay. Now what?
So now you have a point, and you have the slope from our last problem. So you could use point slope form and figure out
Also, f prime of 1 was minus 1/9. And what was that?
That's the slope.
Slope at x equals 1. This means this is our m in the y equals mx plus b, right?
Yes.
So now we'd be able to use, there are various ways to continue here, but personally I like the point slope form. Y minus y1 equals mx minus x1. So this is the point slope form. And now you just plug in all the values. So this means I know my y value is 1/3, my slope is minus 1/9, and my x input is 1. And so that's the actual equation of the tangent line. Now, at this point, I don't think I told you why it's actually, well, I might have mentioned it, but I'm going to do more examples in future lectures. Why finding such a line is important. But you should know at this point, at least, how to find such a line, right? So if I gave you a random function and asked you to find the equation of the tangent line at a certain point, you should actually be able to do that. If I give you a certain function and I ask you, what is the slope of this function at a certain point, or what is the derivative of a function at a certain point, and compute this using the limit definition of the derivative, you should be able to do that. Yeah, so examples like these are very important. And yeah, so that'd be the actual equation of the line. And that's the equation of the line in the point slope form. Of course, you could rewrite it in slope intercept form, but I'd probably only waste time doing that if the answer responses were in that form and you had to actually convert it to actually make the comparison. But in general, unless I specifically require a certain form of a line, you won't have to write it in a specific form. I like using the point slope form, but you don't have to use it. And that's because once you use the point slope form, everything is self-contained. If you use the y equals mx plus b form, you'd have to realize that you have to plug in the y, the m, and the x. You'd have to solve for the b, and then you have to go back and recopy the equation, plugging in the b, but not plugging in the y and the x, right? So if you want to do that, you can do that as well. But yeah. So those were the main concepts. Limits, we briefly spoke about continuity, and we spoke about derivatives and tangent lines. And I mean, just for the sake of completeness, if I were to ask you about the average rate of change, on the interval AB. How is that defined? Do you guys remember average rate of change?
Would it be f of b minus f of a all over b minus a?
Right, that's called the average rate of change. And you can think of this as the slope of the secant line. So this is just how a graph changes on average. You can think of a derivative as the instantaneous rate of change. So for a derivative, I can put parenthetical here, instantaneous. So there is something like an average rate of change, how you change over some interval. But the derivative talks about how fast you're changing at a specific point. So this is, if you have a function, f of x, and this is a, this is b, then that expression actually tells you about the slope slope of this line. So if I were to go back to the same function we had earlier, so let's say my f of x was 1 over x plus 2, and I ask you what is the average rate of change? On, let's say I gave you the interval 1 comma 3. Then this is just f of 3 minus f of 1 over 3 minus 1. What is f of 3 here?
One-fifth.
F of 1 is 1/3, and all that is divided by 2. And there are a couple ways you could do this, but you can multiply and divide by 15. This would give me 3 minus 5 over 30. So yeah, that's average rate of change. I mean, we're pretty much out of time, but I think we touched on all the topics. Any other questions so far? Issues that you were having when going over the lectures?
I have a quick question on homework.
Okay.
So for the homework, I know that like it says that we get like for pretty much every problem unlimited attempts. So does that mean if we do it one time and we get it wrong, but then we do it again and we get it right, we get credit for getting it right?
Yes.
Okay.
Yeah, it'll grade the last attempt.
Okay. Thank you.
Yeah. So hopefully that was helpful, cleared up some misconceptions. Very common misconceptions with limits is the fact that people mix up being defined at the point with the limit. You need to know that the limit doesn't care about being defined at a certain point. We spoke about what limits at infinity means, and these are the topics. Yeah.
Can you just briefly go over the derivative again?
What you need to
That
know about the
problem.
derivative is the definition. Well, you should know what it means conceptually, but what you need to know is the definition of the derivative, which so far, this is the definition you're going by. And of course, later on, we will be doing shortcuts and etc. because going through this is kind of annoying all the time. But that's for future lectures. So for derivative, you should know the definition. You should know how to compute a derivative using the definition, which is what we've talked about here. And you should know that once you actually get that answer, what does that answer mean? What can you use it for? And basically, you would use that answer to figure out the slope of the tangent line at a certain point. So if I told you, here's a function, I want to find the tangent line at a certain point, then the slope of that line comes from the derivative. And of course, once you know the slope of a line and you know a point that it passes through, you should be able to find the equation of the line. Does that cover? So that's the summary of what you should know and what you should be able to do. Does that cover what you wanted to ask? Is there something about the derivative you didn't get?
No, that's good. Thank you.
Yeah. So what you should need to know is the limit definition of the derivative. You should know that by heart. You should know how to plug stuff into that definition and compute it and simplify and calculate. And you should know how to find the slope of a function at a certain point. You should also know how to find the equation of the tangent line to a function at a certain point. And with that, you would know everything. Yeah, so
I have a question.
Yes.
It's about continuity. So I still don't understand how at one point it can be continuous and not continuous at the same time. I'm a little confused on that.
How at one point you can be continuous and not continuous? You can't do that at the same time. So
Well,
for example,
yeah, I phrased that wrong.
So f is continuous versus continuous at a point. Right. Basically, the idea is continuous is a local phenomenon. So continuous is a local phenomenon. So I can have a function that's doing this thing here and there, and I can say f is continuous over here. And I can also say that f is continuous over here. However, if I were to find this specific x value, I would be able to say f is not continuous at x. But from that, I would be able to say f is not continuous in general. So this continuous just means whenever you're in the domain, you are not at a point of discontinuity. And so for this example, you'll notice that the domain of f of x is all real numbers. But we're not continuous at x equals, let's put in a specific number here, 2. So f is not continuous. However, I could say f is continuous at all points where x not equal to 2. Right? So saying something is continuous means that there is no break, there's no gap, there's no disruption. At every single point, the limit will equal the value of the function once we're in the domain. If we don't have that, right? So for example, x equals 2 is in the domain because it's right here. However, the limit as I approach 2 does not exist, which means I'm not continuous at 2, which means f is not continuous in general. Now I can focus on one region versus another. Like I can look in this region right here and I'd be able to say, oh, in that space, f is continuous. But if I were to look at a larger interval like over here, I would say it's not continuous over there. Does that help?
Yes, thank you.
Yeah. So you pretty much use the word continuous with no qualifiers if you are continuous in a global sense. But you can also talk about regions. You can say f is continuous on the interval 1, 2, but it is not continuous on the interval -5, 7 or whatever, right? So you can talk about continuity in a local sense. However, if you find that no matter where you look in the domain, as long as your interval is in the domain, you have continuity, that's when you say a function is continuous in general. However, a function can mess up at specific points. And I can ask you when to determine, is it continuous at this point? Is it continuous on this interval? So basically, if I ask you if a function is continuous on an interval, basically you want to know that at all points in that interval, there's no hole or jump or gap or break. And that means the limit equals the value of the function at all points, which basically means in a picture, it's a solid line, right? And there's no jump or hole or gap. So we'll wrap up there. I will post this video and the lecture notes. And of course, if you have any questions over the weekend, you can email me or whenever, I guess. And we can maybe even set up some office hours if you find that necessary. But hopefully today's review was kind of giving you an idea of where you kind of should be. I know several of you watched these lectures very recently, so you probably don't even know fully what you don't know yet. You have to actually practice a few problems. So I would get on that, practice a few problems, do all the online homework up to the point where it asks you about finding tangent lines and see are you getting everything. And if you are getting everything like that, you understand all the concepts, all the definitions, you should be fine.
Thank you.
Okay. We're a little over time, so we're going to wrap up. Have a good
Thank
day,
you.
everybody.
You too.
Thank you.
Have a good week. Have a good weekend.
Thanks.
And I'll see you guys in the next one. Ciao.